All right, next we're going to have Moses Liskov telling us about extreme consensus.
Hi. So this is a joint work with Megumi Ando at MITRE. I'm talking about this in terms of Byzantine fault tolerance. Byzantine fault tolerance, of course, is just another way of saying security against adaptive adversaries in a multi-party situation. So a single adversary can adaptively corrupt nodes, and corrupted nodes can send arbitrary messages. We want to deal with this in the asynchronous network model, which means that honest messages can be delayed arbitrarily. We have absolutely no guarantee of delivery. The lower bound that's been proven for doing anything of interest is you need to have the number of nodes greater than 3 times the corruption limit. And some of the key problems in the area are for reliable broadcasting consensus. So that's known for quite some time now. Anyway, if you change the model a little bit, instead of having a Byzantine fault tolerance situation, you deal with an adversary that simply crashes nodes. Then you can do a lot better. You can have a lower bound of n simply greater than 2t, so just an honest majority is enough. And so what we're interested in is the hybrid model. I'm sort of surprised that this thing hasn't come up more in the literature, but in the hybrid Byzantine model, we have an adversary that has the ability to either crash things arbitrarily and let them behave in any arbitrary way, or to simply crash a node, and so it stops sending messages. Corrupted nodes can send messages the adversary's choice. Crash nodes can't send anything. We have up to B corruptions and up to T total crashes or corruptions. There's sort of 2 different thresholds. And our results are that there is a lower bound of n greater than 2t plus b, which actually matches up on both ends. So n greater than 2t, if b was equal to 0, that would indicate the adversary doesn't have any Byzantine corruption, so it's just like the crash tolerance case. And if b equals t, in other words, the adversary can Byzantine corrupt any number of the nodes, then it's just like n greater than 3t. So it actually connects these two. And we also give optimal size protocols for reliable broadcast and consensus. Okay, here's the key principles to think about when you're dealing with Byzantine fault tolerance in an asynchronous network. So remember that you don't have any guarantees about the delivery of good messages. So if there's a message that if you're waiting, then you don't know if the good node just isn't ever going to respond. So you have to deal with things like you can wait for n minus t responses. You can't wait for all the responses. And of the ones that you get a response from, you can argue that, well, at least t plus 1 of them are honest, because n minus t is at least 2t plus 1, and at most t of those can be bad, so there's at least t plus 1 honest nodes. And so if you have the ability in your protocol to make progress as long as there's at least t plus 1 honest nodes, then you should be okay. Okay, what if we had n equals 2t plus b plus 1 nodes in the hybrid Byzantine model? So we can still wait for n minus t responses. That's true still. Of those, at least t plus 1 were honest at the time. Well, n minus t is t plus b plus 1. At most, b of them could have been dishonest when they actually sent their message. So you have at least t plus 1 that were honest when they sent their message, but only b plus 1 of them must remain honest later. And so we have this duality problem. So basically, b plus 1 honest nodes must actually be sufficient to force progress. Okay, so I'm going to give you the overall view of what it looks like to do this consensus protocol. Basically, you have a sequence of rounds and oops, I want to go forward, yes. And each round consists of running 2 major protocols. There's a vote protocol, which tries to determine if there is some kind of clear majority for an actual value to output. And there's a global coin, which produces some random, sort of agitation so that the thing doesn't settle into some sort of static pattern forever. And basically, if the vote protocol is successful, then that creates your output. Otherwise, honest nodes will go with the output of the global coin for their next round, and so eventually you're going to make progress towards something. And I just want to give you a little bit of detail about how the vote protocol translates, because there's other details in the paper, but this one I can actually give you. So this is I'm not going to go into the details, but this is the protocol from Kennedy and Rabin for the vote protocol. And one of the key pieces of logic here is the size of the intersection of 2 honest nodes' views. Remember, they each wait for n minus t. So the intersection size is n minus 2t. And the fact that that's at least t plus 1 guarantees that if one of them sees everybody saying the same thing, then the other one sees a majority of them saying the same thing. Okay. Great.